Section 5.3, we're continuing our study of system of linear equations and how to use matrices to solve these systems of equations. These are special cases to where we can have an overdetermined system or an underdetermined system. And that has to do with the number of variables and the number of equations that we're working with. Now, geometrically, the number of variables that we have, x, y, z, correspond to the number of dimensions that we have. And dimensions, so if we're in 2 dimensions, if we have an x and a y, that corresponds to a line. If we have 3 variables, x, y, z, then we're in 3 dimensions, we're working in terms of a plane. The number of equations corresponds to the number of objects. So if we have 2 equations and 2 variables, then we have 2 lines, as in this 2 by 2. Now, if we have 3 equations and 3 variables, we're working with 3 planes. Planes are a little more difficult to visualize because we're in 3 dimensions, but I've got 3 planes here in 3 different colors, blue, green, and red. And you can see how they intersect. And it's 2 by 2, right? They intersect at exactly 1 point, right? So we have a unique solution. In this 3 by 3, we also have a unique solution. You may want to draw this out yourself and play around with it just to help solidify this concept. But if you have 3 planes, they will intersect in exactly 1 point, and they intersect right here. The blue and the red, they intersect in this line, but then the green plane intersects that line in exactly 1 point. All right, now if the number of equations is greater than or equal to the number of variables in a linear system, then there are a few things that could happen. The 2 examples that I've drawn here, that's when the number of equations are equal to, but this also applies if the number of equations are greater than. You can have a system that has no solution. You can have a system that has exactly 1 solution, or you can have a system that has infinitely many solutions. We're going to look at that geometrically. The 2 cases that I've listed here satisfy the second part, is that the system has exactly 1 solution. When we talk about the number of solutions, we're talking about the number of ordered pair in the intersection of our 2 things, whether we're talking about equations or planes. And so this 2 by 2, we have exactly 1 point of intersection. So there's a unique solution, exactly 1 solution. In this 3 by 3, we have exactly one solution because there's 1 intersection. And so that's the second part. Now, what if a system had no solution? What would that look like? Well, if we had 2 lines that are parallel, they never intersect, that would be a case where the system has no solution. We could say the same thing about the 3 by 3. And if we had 3 planes that are parallel, and all 3 of them would not necessarily need to be parallel, just that they don't intersect. Not all 3 planes are intersecting. You know, we could have something like this. If 2 planes are parallel, that's enough to make the system have no solution. And so that's a no solution case. What about the system having infinitely many solutions? Well, we've seen this in a previous section, to where if you have 2 equations that have the same graph, or they overlap everywhere, then you have infinitely many solutions because you have an infinite number of points in the intersection. And the same thing happens with the 3 by 3. All right, if you have 3 planes, all right, 3 equations that result in the same plane, then you would have infinitely many solutions. Now, the same thing could happen if you have if the number of equations are greater than or equal to the number of variables, right? We're just adding lines or planes to this. If we were to have 3 lines in this case, right, we could still have exactly 1 solution, right, if it intersects that point of intersection. We could still have no solution, right, because we don't have a common point of intersection with all three lines. And we could also have infinitely many solutions if that third line coincided with the other two. And the same thing with a 3x3. If we were to add an extra equation, if we had 4 equations and 3 variables, then we could still get exactly one solution if that plane is going to be difficult to draw and make it visible. But we could draw another plane so that it intersected at that same point of intersection that we had with the other 3. If we added another plane here, right, that would still be no solution because you don't have a common point of intersection with all 4 planes. And for this infinitely many solutions, if that 4th plane coincided with the other 3, you would still have infinitely many solutions. Okay, so if the number of equations is greater than or equal to the number of variables, we could have any of those 3 cases. In the previous video, we focused on that second case to where the system has exactly 1 solution. In this video, we want to focus on the number 1 and number 3, to where the system has no solution or the system has infinitely many solutions, so that we can see what that looks like when working with the matrix. If we have fewer equations than variables, then the system either has no solution or infinitely many solutions. This is an underdetermined system. That should say underdetermined, because we do not have enough equations for the variables. It's either going to have no solution or infinitely many solutions. We're going to see an example of this momentarily. All right, first, let's take a look at some cases to where we have the same number of equations as variables. We have, in this case, 3 variables, 3 equations. So there's 3 possibilities. We can either get no solution, exactly 1 solution, or infinitely many solutions. We've already looked at the case where we have exactly 1 solution. So our 2 examples here are going to have either no solution or infinitely many solutions. So we're going to first write this as a matrix. We're going to throw out the variables, keep the numbers 1, 2, -3, -2, 3, -1, -2, 1, 2, 3, -5, and -3. All right, so we want the first entry in the first column to be 1. We already have that. So next we move to forcing the other entries in the first column to be 0. We do that by adding the additive inverse to row 2. That would be a -3 times the row with a 1. All right, so -3 times row 1. And row 3 minus 2 times row 1. All right, so row 2 minus 3 times row 1. 0, -7, 7, 7. Zero, -7, 7, 7. Same thing with R3. Times -2. Row 1, that's -2, -4, 6, and 4. So that is 0, -1, 1, 1. Now you may or may not notice here that row 2 and row 3 are now multiples of each other. Right? Row 2 is the same thing as row 3, just multiplied by 7. Okay, that's going to come into play. But now we want the column 1 is done, so we move to the second column. We want the second entry in second column to be 1. So we will multiply by the multiplicative inverse. And so we're multiplying by negative 1/7 times row 2. That is 0, 1, negative 1, negative 1. Now that we've got the 1, we want everything else to become zeros. So we will do that by adding row 1 to the additive inverse of row 2, and row 3 plus the additive inverse times row 2. So row 1 plus negative 2 times row 2. That's 1, 0, negative 1, 0. And then row 3 plus 1 times row 2. Now look what's going to happen here. We've got 0, 0, 0, 0. So column 2 is done. So now we would normally move to column 3, but there is no way to make this 0 become a 1. So that means that we are done here, right? This third row is a row of all zeros. This is still considered to be row reduced form because it satisfies those 4 criteria for the row reduced form. You can go back and check that, right? So this is our final form. Okay, so what does this mean? So this, looking at the row with all zeros, right? If it's a row of all zeros, the coefficient side and the right-hand side are both zeros, that means we're going to have an infinite number of solutions. Writing this out by rows, we have 1x plus 0y minus z equals 0. And second row, 0x plus 1y minus z equals negative 1. And then the third row we don't care about because it's all zeros. And so notice here that x and y can be written in terms of z. All right, if we were to solve for x, right? So x is equal to 0, it is equal to z. Y is equal to z minus 1. So z we say is the independent variable because z can equal anything since we have that 0 in that third position in the third column. Z is the independent variable. X and y are the dependent variable. X and y depend on what z is. So z is our free variable. Writing this as an ordered pair, as that ordered triplet. Right? So z can be anything. So x is equal to z, y is equal to z minus 1, and z can be anything. Right? This would represent our solutions. Right? We have an infinite number of solutions, and our ordered triplets would be in this form, right? So when z is equal to 1, one solution would be 1, 0, 1. If z were equal to 2, a solution would be 2, 1, 2. All those ordered triplets would satisfy our system of equations. Okay, so this would be our final answer. Now, the final answer is not infinitely many solutions. That's true, but that doesn't describe our solution. This describes our solution. Okay, that's the case with infinitely many solutions. Now we'll see the next example, same procedure, but we should get a no solution case for that. Okay, in this case, we'll set this up the same way, writing out our matrix. Okay, we'll begin with the first column. That first entry is already 1, so we want to set everything else in that first column to be 0. We do that by adding to row 2 the additive inverse times row 1, and row 3 adding the additive inverse times row 1. All right, so row 2 minus 3 times row 1. Negative 3 times row 1, that's negative 3. All of these are negative 3s. Makes it easy. Now we add this, 3 plus negative 3 is 0, and then negative 4, and 1. And then our 3 minus row 1. Minus row 1. 0, 4, 4, and negative 2. And an observation here, row 2 and row 3, at least the coefficient side, are multiples of each other, and it is, but not the right-hand side. All right, so in the case to where the coefficients are multiples of each other, but not the right-hand side, that's going to be a no solution case. You may be able to recognize that early on. If not, we can continue moving on, and it will be more evident as we continue. So now the first column is done. So we move to the second entry in the second column. We want that to be 1. We do that by multiplying by the multiplicative inverse, which is a negative 1/4 times row 2. That is 0, 1, 1, negative 1/4. And we want everything else in the second column to be zeros. We want that to become a 0, and that to become a 0. So we will add to row 1, negative 1 times row 2, and to row 3, we will add a negative 4 times row 2. Row 2 stays the same. And row 1 minus row 2 is 1, 1, 1, 1, 0, negative 1, negative 1, positive 1/4. That's 1, 0, 0. I'll say that's 5/4 here, right? How am I doing that? I'm multiplying by the denominator. So think of 1 as 1 over 1, multiply top and bottom by 4, right? So that 1 can be thought of as 4/4. 4/4 plus 1/4 is 5/4. And then row 3 minus 4 times row 2. Negative 4 times row 2 is 0, negative 4, negative 4, and positive 1. Or negative 4 times negative 1/4 is a positive 1. We'll add these together to get 0, 0, 0, negative 1. And column 2 is done. Typically, we would move over to column 3, but that third entry in column 3 is 0, and there's no way that we can make the 0 become a 1 without messing everything else up. Okay, I'll just say that we can turn that 0 into a 1, but that would mess up our other entries in the previous columns. Okay, so when we have a 0 in the entry that we're trying to make a 1, right, we're going to say that cannot be done. So that means that this is in row reduced form. Okay, now look at that last column. Right, I mentioned that before, right? Or when we have multiples, right, we said that the second and third row of the coefficients are multiples. That means that we're going to get a row of zeros in the coefficient side at least. And we said that the second and third entry on the right-hand side are not multiples, the same multiple. So we're not going to get a 0 on the right-hand side. So what this is telling us is that 0 is equal to a -1, which that's a false statement, right? So that means that there is no solution here. All right, so that means our 3 planes do not intersect at a point. Right? You may have 2 planes that intersect, but not all 3 planes intersect together. So in this case, we have a no solution for our answer.